theoretical physics has made its worst prediction. It is not off by a little. It is wrong by a number so vast it defies human imagination. This is the vacuum catastrophe, and it means our two most successful descriptions of reality are fundamentally broken. At the heart of the crisis is a concept called vacuum energy. Our best theory of the small quantum field theory calculates what the energy of empty space should be. The number it produces is astronomically huge, yet when we look out at the cosmos and measure the actual energy content of the void, we find a value so tiny it is almost nothing. The difference between prediction and reality is not double or tenfold. It is a factor of 1 followed by 120 zeros. That is a discrepancy of 120 orders of magnitude, the largest error in the history of science. This chasm reveals a deep crack in the foundation of modern physics, where quantum mechanics and Einstein's theory of gravity meet and fail completely. By the end of this exploration, you will understand why this single number threatens to rewrite our cosmic rulebook and what radical ideas might mend it. We will see how the nothingness of space became a seething quantum ocean and why the universe's fate hinges on a value we cannot explain. What does it feel like when science stares into an abyss this profound? To grasp the scale of this error, we must first understand what empty space truly is. For centuries, the classical view of a vacuum was simple. It was pure nothingness, a complete and utter void. If you removed every atom, every particle, every shred of matter and light, what remained was a perfect, silent emptiness. This was the stage upon which physics played out, an inert backdrop that did nothing and was nothing. It was the definition of zero, but the quantum revolution shattered that picture entirely. In the quantum world, nothingness is the most active place in the universe. The vacuum is not empty. It is a seething, bubbling, dynamic medium, alive with potential. This radical shift comes from a fundamental rule called the Heisenberg uncertainty principle. In essence, it states that on the tiniest scales, certain pairs of properties like energy and time are linked in a cosmic trade-off. You cannot pin both down with perfect certainty. For a fleeting instant, a significant amount of energy can simply appear out of nowhere, as long as it disappears again almost immediately. This loophole in reality means the vacuum is not still. It is a quantum foam. Pairs of virtual particles and their antiparticles constantly flicker into existence, borrowing energy from the void and annihilating each other back into nothingness before the universe can notice the debt. It is a perpetual, chaotic dance of creation and destruction happening everywhere, all the time, even in the space between the atoms in front of you. The lowest possible energy state of a quantum field, its ground state, is therefore not zero. It is a baseline hum of activity called zero-point energy. Think of it like a guitar string. Even when it is not being played, even in its lowest energy state, it still vibrates subtly. It cannot be perfectly still. The quantum fields that make up our reality are like that, forever vibrating with this irreducible energy. This is not just a theoretical curiosity. We have measured it. The Casimir effect demonstrates this beautifully. If you place two incredibly smooth, neutral metal plates extremely close together in a vacuum, they are gently pushed toward each other. Why? Because the space between the plates is so narrow, it restricts which wavelengths of virtual particles can flicker into existence. Outside the plates, the full spectrum of quantum jitter continues unabated. The greater pressure from outside pushes the plates together. We have literally seen the force of empty space. Another proof is the Lamb shift, a tiny but measurable change in the energy levels of an electron in a hydrogen atom, caused by its constant interaction with the quantum vacuum. These are not guesses, they are experimental validations. The energy of the vacuum is a real, physical thing with real, physical consequences. It is the hum of the universe itself. And according to our best quantum calculations, that hum should be deafening. But this quantum hum has a price tag, a specific energy density that our most powerful framework, quantum field theory, can calculate. The process is conceptually straightforward, yet it leads to a number of staggering proportions. Think of every fundamental field in the universe: the electron field, the photon field, the quark fields, and all the others. Each one is like that vibrating guitar string, humming with its own irreducible zero-point energy. To find the total energy of the vacuum, you must add up the contributions from every single possible mode of vibration for every single quantum field. And this sum does not stop at the particles we know. It extends upward through every possible frequency to energies far beyond what our particle colliders can probe, all the way to the theoretical limit where gravity becomes as strong as the other forces, a scale known as the Planck energy. This sum, in principle, runs to infinity, which is obviously nonsensical. So physicists introduce a cutoff, a reasonable upper limit where our current theories might break down. Even being incredibly conservative and cutting the calculation off at a much lower energy scale associated with known physics, the result is colossal. The predicted energy density of empty space comes out to roughly 10 to the power of 112 ergs per cubic centimeter. To call this number astronomical is a profound understatement. It represents an energy so dense, so unimaginably concentrated, that if it were real, the universe as we know it could not exist. This is not a wild speculation or a fringe idea. It is the direct, almost naive output of applying our incredibly successful quantum field theory to the vacuum itself. The mathematics that perfectly predicts the magnetic moment of an electron or the outcome of particle collisions, when asked about the energy of nothing, gives us an answer that is catastrophically, undeniably wrong. Yet when we look out at the cosmos and measure the energy content of the void, we find a whisper instead of a roar. This measurement comes from cosmology, the study of the universe as a whole. For decades, astronomers have been meticulously charting the expansion of the universe. They do this by observing distant beacons of light, particularly a special kind of exploding star called a Type 1, a supernova. These stellar explosions have a known, consistent brightness, making them perfect cosmic mile markers. By measuring how bright they appear from Earth and the redshift of their light, scientists can calculate not just their distance, but how fast the universe was expanding when that light was emitted billions of years ago. In the late 1990s, two independent teams made a shocking discovery. They expected to find that the expansion of the universe was slowing down over time, pulled back by the collective gravity of all matter. Instead, their data revealed the opposite. The most distant supernovae were fainter than expected, meaning the universe is expanding faster today than it was in the past. Something was pushing galaxies apart, a mysterious repulsive force acting against gravity on the largest scales. This force was given a name: dark energy. The simplest and most consistent form of dark energy is a constant energy density inherent to space itself, a property of the vacuum that does not dilute or weaken as the universe expands. Think of it this way: if you have a box full of matter and you double the size of the box, the density of the matter inside halves. But if the box contains this form of dark energy, its energy density remains exactly the same, no matter how big the box gets. As more space is created, more of this constant energy appears within it, leading to a runaway, accelerating expansion. Through decades of observation by missions like the Planck satellite, which mapped the faint afterglow of the Big Bang, cosmologists have pinned down the value of this dark energy density with incredible precision. It is approximately 10 to the power of -8 ergs per cubic centimeter. This number is extraordinarily small, almost but not quite zero. It is the measured energy of the cosmic vacuum. So we have two numbers, both claiming to describe the same thing. From quantum field theory, a roaring ocean of energy, 10 to the 112. From cosmology, a faint, persistent hum, 10 to the -8. The confrontation is direct, and the gap between them is not just a gap, it is the widest canyon in all of science. This is a discrepancy of 120 orders of magnitude. To understand what that phrase truly means, we must hold the two numbers side by side. The quantum calculation suggests a vacuum energy of roughly 10 to the power of 112 ergs per cubic centimeter. The cosmological measurement finds a value of about 10 to the power of -8. The difference between them is not found by subtraction, but by division. You must divide the enormous prediction by the tiny observation to see the gap. That divisor is a 1 followed by 120 zeros, a factor of 10 to the 120th power. The human mind cannot intuitively grasp a number this large. It exists in the realm of pure mathematics, a scale so vast it breaks all our everyday analogies, but we can try. Imagine the predicted vacuum energy, that roaring quantum ocean, was given physical size. Let us say it was as large as our entire observable universe, a sphere over 90 billion light-years across, containing every galaxy, every star, every planet we could ever hope to see. Now, what would the actual, observed vacuum energy be in that same scale? It would be smaller than a single proton, not a speck of dust, not a grain of sand, not even an atom. It would be a subatomic particle, lost in the cosmic immensity of its own prediction. This is not being off by a mile. This is predicting a mountain and finding a grain of sand. It is not a minor calibration error or a missing decimal point. It is a complete and utter failure of two foundational theories to agree on the most basic property of reality, the energy of empty space. No other prediction in the history of physics has been wrong by such an incomprehensible margin. This is why it is not called a problem or a puzzle. It is called the Vacuum Catastrophe. It has earned a more solemn title, the worst prediction ever made. This staggering mismatch is a catastrophe because it exposes a foundational crack in physics itself. The problem is not that the quantum calculation is difficult. It is that its results should have a direct, dramatic, and immediate consequence in our theory of gravity, Einstein's theory of general relativity. In that theory, energy and mass are what curve the fabric of spacetime, creating what we perceive as gravity. The vacuum energy, this seething quantum hum, is a form of energy. Therefore, it must act as a source of gravity. It should curve spacetime. Einstein actually included a term for this possibility in his equations, a fudge factor he called the cosmological constant, representing a uniform energy density of the vacuum. For decades, it was considered a mistake he retracted. Now we know it is real, but its value is the heart of the crisis. The vacuum energy predicted by quantum field theory is not just another number to plug in. It is a specific instruction for how spacetime should behave. If that enormous predicted value were correct, the cosmological constant would be correspondingly enormous. The gravitational effect of such a dense energy filling all of space would be immediate and violent. Spacetime would be curved so intensely that the universe would have either blown itself apart in a fraction of a second after the Big Bang, or collapsed back in on itself just as quickly. Stars, planets, and life would have had no time to form. The cosmos would have been stillborn. We are here discussing this, which means that did not happen. The cosmological constant we actually observe is minuscule, allowing for billions of years of gradual cosmic evolution, so we are left with a philosophical chasm. The fact that we exist to measure a value 120 orders of magnitude smaller than the prediction points to one of two unsettling possibilities. The first is that our understanding is deeply, fundamentally flawed. Our two most successful theories, quantum field theory and general relativity, are talking past each other in a critical way, revealing a missing piece of physics at their intersection. The second possibility is even more jarring. It suggests that for some reason, the positive and negative contributions from the quantum foam cancel each other out with almost, but not quite, perfect precision. They balance to a value so infinitesimally close to zero, yet distinctly not zero, that it allows our universe to exist. This degree of fine-tuning seems impossibly lucky, as if the cosmos were calibrated with exquisite care. Either our theories are broken or the universe appears improbably arranged for life. Both conclusions are profoundly disquieting for science, which seeks natural, inevitable explanations, not magical cancellations or incredible coincidences. This is why the vacuum catastrophe is more than an error. It is a direct challenge to our comprehension of reality, forcing us to question whether we have truly grasped the rules of the void. The story of this cosmic era has deep roots, stretching back to the very beginning of modern cosmology. In 1917, Albert Einstein was applying his new theory of general relativity to the universe as a whole. The prevailing scientific belief at the time was that the cosmos was static, eternal, and unchanging on the largest scales. Stars might move within it, but the overall fabric of reality was fixed. Yet when Einstein solved his own magnificent equations, he found a problem. They predicted a dynamic universe, one that would either be expanding or contracting under the relentless pull of gravity. A static solution simply did not emerge naturally. To reconcile his theory with the accepted view of a steady cosmos, Einstein made a small but profound modification. He introduced a new term into his equations, a fudge factor he called the cosmological constant, represented by the Greek letter lambda. This constant represented a uniform, repulsive energy inherent to the vacuum of space itself. It acted as a kind of anti-gravity, a gentle outward push that could precisely balance the inward pull of all the matter in the universe, creating the static, unchanging cosmos everyone believed they lived in. For Einstein, it was a necessary evil, a mathematical trick to preserve the accepted model of reality. Then, in the late 1920s, the astronomer Edwin Hubble made an earth-shattering discovery. By observing distant galaxies, he found their light was systematically shifted toward the red end of the spectrum. This redshift indicated they were all moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static at all. It was expanding. Einstein immediately realized his cosmological constant was no longer needed. With great regret, he reportedly dismissed it as his greatest blunder, an unnecessary complication he had inserted out of a misguided desire for a certain kind of cosmic order. He removed lambda from his equations, and for decades the idea of a vacuum energy was largely forgotten, a curious footnote in the history of a genius's mistake. The irony, of course, is breathtaking. Nearly 70 years after Hubble's discovery, astronomers found the expansion of the universe was not just continuing, it was accelerating. Something was pushing galaxies apart faster and faster. The simplest explanation for this cosmic acceleration was the resurrection of Einstein's discarded idea, a positive cosmological constant representing a tiny, constant energy density of empty space. The blunder was not the concept itself, but his reason for introducing it and then abandoning it. The universe did have a cosmological constant, but its value was not tuned to create a static cosmos. Instead, its incredibly small, non-zero value was shaping the ultimate fate of everything. This historical twist adds a profound layer to the catastrophe. The cosmological constant lambda, once a fudge factor, is now a central pillar of our standard model of cosmology. Its measured value is precisely what allows for the accelerating expansion we observe. Yet when we ask our other great theory, quantum field theory, to calculate what lambda should be from first principles, it gives us an answer that is not just a little off. It is off by a factor of 1 followed by 120 zeros. The historical journey from blunder to cornerstone only heightens the mystery. We have identified the key player, the energy of the vacuum, but its strength defies all explanation, revealing a fundamental disconnect at the very heart of physical law. Faced with a number this preposterous, the instinct of any physicist is to look for a mistake in the calculation. Perhaps we are adding up the quantum jitters incorrectly. The most straightforward fix seems obvious. Our sum runs to infinity because we are including every possible frequency of vibration, up to unimaginably high energies. But what if unknown physics, some new principle or particle, acts as a ceiling? What if contributions from energies above a certain point simply do not count? This is the idea of introducing a cutoff. We say, let us only add up the quantum fluctuations up to a reasonable energy scale, a point where our current theories might start to break down and ignore everything above it. It is a pragmatic approach, like deciding you only need to measure the waves on the ocean's surface, not the turbulent currents miles below. A natural candidate for this cutoff is the electroweak scale, the energy at which the electromagnetic force and the weak nuclear force merge into a single unified force. This is a fundamental milestone in particle physics, around 246 gigaelectronvolts. It is well within the realm we understand, so we perform the calculation again, but this time we stop the sum right there. We only include the quantum foam's activity up to the electroweak scale. The result is a prediction for the vacuum energy density that is, admittedly, much smaller than the original catastrophic number. But here is the devastating catch. Even with this dramatically lowered ceiling, the predicted value is still about 10 to the power of 55 ergs per cubic centimeter. Compare that to the cosmologically observed value of 10 to the negative 8. The gap has shrunk from 120 orders of magnitude to 55. This is not a solution. Being wrong by a factor of 1 followed by 55 zeros is still being catastrophically, incomprehensibly wrong. You could repeat this exercise with other plausible cutoffs at the quantum chromodynamic scale or even lower, and the problem persists. The vacuum energy predicted from even the most conservative, low-energy quantum physics we know is still dozens upon dozens of orders of magnitude larger than what the universe allows. This tells us something profound. The vacuum catastrophe is not a technical glitch. It is not a problem we can fix by tweaking an upper limit or refining a complex integral. The chasm between prediction and observation is so vast that it persists across many, many orders of magnitude. It is robust. This means the solution cannot be a mere adjustment to the calculation. It demands something far more radical, a fundamental shift in how we think about nothingness, energy, and gravity itself. The naive fixes have failed, leaving us staring into a deeper mystery. One of the most elegant ideas ever proposed to tame the quantum vacuum came from a concept called supersymmetry. This is not just another particle theory. It is a profound mathematical symmetry that suggests a deep and beautiful partnership at the heart of reality. For every known particle in the standard model, from quarks to electrons to photons, supersymmetry predicts the existence of a superpartner. Fermions, the matter particles, would have bosonic partners. Bosons, the force carriers, would have fermionic partners. An electron would have a selectron. A quark would have a squark. The photon would have a photino. This doubling of the cosmic roster was not proposed just for fun. It solved several nagging theoretical problems at once, and crucially, it offered a potential escape from the vacuum catastrophe. Here is why. Remember, the monstrous vacuum energy prediction comes from adding up all the positive contributions from the quantum jitter of every field. But in a perfectly supersymmetric world, these contributions would come in pairs. For every particle's quantum fluctuation adding a positive push, its superpartner's fluctuation would provide an equal and opposite negative pull. They would be perfect mirror images canceling each other out with exquisite precision. In one sweeping, beautiful move, the deafening roar of the quantum foam would be silenced. The vacuum energy would be exactly zero. For a time, this seemed like a miraculous solution. It was not a fudge or a cutoff. It was a fundamental principle of nature that demanded the cancellation, offering a natural, elegant reason why empty space could have no inherent energy. The vacuum catastrophe would be solved before it even began, because the theory would predict zero, and zero is at least in the right ballpark as the incredibly small value we observe. Supersymmetry promised to heal the rift between quantum theory and gravity, not with a patch but with a deeper harmony. It was physics at its most hopeful, suggesting that behind the chaos, a perfect balance awaited discovery. But the universe, as it so often does, had other plans. If supersymmetry is a real feature of nature, it must be a broken symmetry. We know this because we have not found a selectron or a squark sitting next to an electron in an atom. These superpartners, if they exist, must be incredibly massive, far beyond the energies our most powerful colliders can produce. The symmetry is hidden or broken at the energy scales we inhabit. And that breaking is the fatal flaw in this elegant rescue plan. The mechanism that breaks supersymmetry, that gives the superpartners their heavy masses while leaving the known particles light, inevitably injects energy back into the vacuum. Think of it like a perfectly balanced scale. Supersymmetry in its perfect form keeps the scale level at zero, but to hide the partners, you have to place a weight on one side. That weight represents the energy of symmetry breaking. This energy then becomes the new contribution to the cosmological constant. When theorists calculate the likely scale of this breaking, based on solving other problems like the hierarchy of particle masses, the number they get is, once again, astronomically too large. Typical models suggest a vacuum energy density from broken supersymmetry around 10 to the power of 44 ergs per cubic centimeter, compared to the observed 10 to the negative 8. That is a discrepancy of 52 orders of magnitude. So yes, supersymmetry brings the error down from 120 orders of magnitude to a mere 52. This is an improvement, but it is like reducing the distance to the nearest star from 1,000 light years to 500. You are still impossibly far from your destination. The fine-tuning problem returns with a vengeance. Why would the breaking mechanism leave behind a residue of vacuum energy that is 52 orders of magnitude smaller than its natural scale? Supersymmetry, for all its breathtaking beauty, does not solve the vacuum catastrophe. It merely softens it, transforming an unimaginable disaster into a merely incomprehensible one. The haunting question of fine-tuning remains, leaving physicists to wonder if an even deeper, more hidden principle is at work. When no physical mechanism can explain such improbable fine-tuning, some theorists turn to a profound and controversial philosophical shift. This is the Anthropic Principle, a line of reasoning that flips the entire problem on its head. It suggests we are asking the question backwards. We should not wonder why the cosmological constant is so perfectly suited for life. Instead, we must recognize that we can only ask the question in a universe where it is. The fundamental constants of nature, including the energy of the vacuum, are not inevitable. They are, in this view, arbitrary, but if they were even slightly different, the universe would be sterile. No atoms would form, no stars would ignite, no planets would coalesce, and no observers would ever arise to ponder the mystery. We exist, therefore the constants we measure must lie within the narrow, habitable window that allows for our existence. It is a cosmic version of the survivor's bias. You do not find fish wondering why the laws of physics allow for liquid water. They only exist where water is liquid. The Anthropic Principle, in its weakest form, is almost a tautology. But when combined with certain modern theories, it transforms into a powerful, if unsettling, explanatory framework. The key ingredient is the multiverse. Concepts like string theory's vast landscape or the model of eternal inflation suggest our universe may not be alone. String theory, a candidate for a theory of everything, may allow for a staggering number of possible stable configurations, perhaps 10 to the 500 or more. Each configuration corresponds to a universe with different physical laws and constants. Meanwhile, eternal inflation paints a picture where our Big Bang is just one bubble in an endlessly frothing cosmic foam, with new universes constantly budding off, each with its own random set of physical parameters. In such a cosmic landscape, every possible value for the cosmological constant, from the catastrophically large to zero and beyond, is realized somewhere. An unimaginable number of universes are born dead, their vacuum energy so immense they rip apart instantly or collapse. Others have a negative constant so large they crunch back into nothingness. But in an infinite array of possibilities, a tiny, tiny fraction of universes will, by pure chance, have a cosmological constant in the habitable range. We do not live in a fine-tuned universe. We live in the only type of universe we could possibly live in. The vacuum catastrophe, from this perspective, is not a problem to be solved by a single elegant equation. It is a selection effect. We are simply residents of one of the extremely rare cosmic neighborhoods where the energy of empty space is quiet enough for galaxies, stars, and thinkers to emerge. For many, this is less a solution and more a philosophical surrender. It exchanges a scientific mystery for a metaphysical one. The multiverse explanation is, by its very nature, profoundly difficult to test. If other universes are causally disconnected from our own, leaving no imprint on our physics, the idea remains in the realm of speculation. To physicists who seek a dynamical mechanism, a specific law or symmetry that uniquely predicts the small value we see, the anthropic argument feels deeply unsatisfying. It explains fine-tuning not by finding a reason, but by invoking an infinite number of unreachable alternatives, making our universe seem like a fortunate accident on a scale beyond comprehension. Yet for others, it represents a necessary expansion of scientific thought, acknowledging that our quest for a single, neat equation for everything might be a local prejudice. The vacuum catastrophe forces us to confront the very limits of explanation. Do we seek a theory that makes our universe inevitable, or must we accept that we are the beneficiaries of a cosmic lottery whose winning ticket is existence itself? This philosophical rift, born from a number 120 orders of magnitude out of place, shows that the crisis of the vacuum is not just about physics. It is about what we expect from our understanding of reality. Another path away from the static vacuum leads us to question its very nature. What if dark energy is not a fixed property of space, but something that changes? This idea resurrects a ghost from the universe's birth. In the first fleeting moments after the Big Bang, a theoretical field called the inflaton is believed to have driven a period of hyper-accelerated expansion, smoothing and stretching the cosmos. That field eventually decayed, its job done. Could a similar but far weaker field be active today, driving the slower acceleration we now observe? This is the concept of quintessence, named for the ancient fifth element beyond Earth, air, fire, and water. Quintessence proposes that dark energy is not the constant hum of the vacuum, but a dynamic, cosmic field that fills space. Think of it not as the static stage, but as a subtle, pervasive weather system moving through the cosmos. This quintessence field is what physicists call a scalar field, meaning at every point in space it has just a single value, a number representing its strength or potential energy. Over cosmic time, this field can slowly roll down a gentle slope in its potential energy landscape. In its early history, when the field value was high up on the slope, its energy density could have been significant, perhaps even dominating the universe for a brief period. But as it rolls down to lower values, its energy density decreases. Today, we would simply be living at a moment when the field has reached a very shallow, low point in its landscape, producing the tiny trickle of energy we measure as dark energy. This offers an elegant narrative. The vacuum catastrophe's impossible number might be a snapshot of the wrong thing. We are not measuring a constant. We are measuring a fading echo. The energy density is small today not because of a miraculous cancellation, but because the clock has run for billions of years and the dynamic field has naturally evolved to a low state. It is a story of cosmic aging where the repulsive force weakening over time. For a moment, this feels like a breakthrough, a way to explain the small number through natural evolution rather than frozen fine-tuning. Yet the relief is short-lived. To make Quintessence work, theorists must sculpt an extremely specific potential energy landscape for the field. The slope must be incredibly flat and gentle to allow the field to roll slowly enough that its energy density has only just become dominant in the recent cosmic past, matching our observations. Furthermore, the initial conditions of the field, its starting value and velocity at the dawn of time, must be set with exquisite care to land us at this precise point today. The problem of fine-tuning has not vanished. It has simply moved. Instead of fine-tuning a static cosmological constant, we are now fine-tuning the shape of a theoretical field and its starting parameters. We have transferred the mystery from a number to a function, from a constant to a curve. While dynamic dark energy models like Quintessence are fascinating and remain an active area of research, they often trade one profound puzzle for another, leaving us still searching for a reason behind the unnatural quiet of our cosmic void. The quiet hum we measure might be a cosmic illusion, a temporary calm hiding a far more profound instability. This brings us to a chilling possibility born from the same mathematics of the vacuum, a theoretical endgame known as vacuum decay. If our universe's vacuum, with its tiny positive energy, is not the absolute lowest energy state possible, then everything we know rests on a precipice. In quantum field theory, the true, most stable state of empty space is called the true vacuum, the absolute rock bottom of the energy landscape. Our universe might exist in what physicists call a false or metastable vacuum, a higher energy state that has been trapped, like a ball resting in a shallow valley on the side of a mountain. For now, it seems stable. It can persist for billions of years, allowing stars and galaxies to form. But it is not truly secure. Given enough time, quantum mechanics provides a terrifying escape route, a process called quantum tunneling. Imagine a ball spontaneously, randomly, burrowing through the mountain instead of rolling over it. In our cosmic reality, this means that somewhere in the vastness of space, a microscopic bubble of the true vacuum could spontaneously nucleate. This bubble would not be made of matter. It would be a region where the fundamental fields of the universe have tunneled to their true, lowest energy state, rewriting the very laws of physics inside it. The properties we depend on, the strength of forces, the existence of atoms, everything would be irrevocably altered. This bubble would then expand in all directions at the speed of light, its boundary a wall of fundamental transformation. From our perspective, there would be no warning. One moment, the universe is as it always was. The next, an invisible wall of redefined reality sweeps through our solar system at light speed. There is no explosion, no sound, no light. The concept of physics as we know it simply ceases to be within the bubble. Atoms would disintegrate, forces would unravel, and the structure of matter would become impossible. It would be an end not with a bang, but with a silent, instantaneous rewrite of existence itself. the probability of such an event occurring in any given region of space in any given year is astronomically small, likely far longer than the current age of the universe. Yet, if the vacuum is metastable, it is not a question of if, but when, over an infinite timeline. This speculative fate ties the abstract crisis of the vacuum catastrophe to a potential, ultimate physical consequence. The stakes of understanding the stability of nothingness could not be higher, for it determines whether our cosmic home is eternally secure or merely temporarily borrowed from a deeper, unknown void. Perhaps the entire premise of the catastrophe is built on a flawed assumption. The calculation that yields the impossible number takes a result from quantum field theory and plugs it directly into the equations of general relativity. This seems logical. Energy curves spacetime, and the quantum vacuum has energy, so it must curve spacetime. But this handoff between theories is not a proven fact. It is an act of faith, a bridge we built because we have no other way to cross the chasm. What if gravity does not see the quantum foam the way we think it does? Our two foundational theories describe reality in utterly different languages. Quantum mechanics deals in probabilities, particles, and discrete jumps. General relativity paints a picture of smooth, curved geometry. We have been forcing a conversation between them, and the vacuum catastrophe might be their way of telling us we are getting the translation catastrophically wrong. The core assumption is that all forms of energy are created equal in the eyes of gravity. But what if the zero-point energy of quantum fields is special? Some physicists speculate that gravity could be blind to it. Think of the quantum vacuum not as a source of gravity, but as the immutable background against which gravity operates. It would be the canvas, not the paint. In this view, the seething quantum activity is real and causes effects like the Casimir force, but it does not couple to the gravitational field. It simply does not weigh anything. This would immediately dissolve the catastrophe. The enormous quantum calculation would be irrelevant to cosmology, and the tiny cosmological constant we measure would arise from some other separate source. It is a radical idea, suggesting a fundamental decoupling between the quantum world and gravity for this specific type of energy. Others propose a less absolute but equally strange possibility. Maybe the zero-point energy does gravitate, but in a highly non-trivial way. When you sum up all those infinite fluctuations, perhaps they organize themselves in a pattern that cancels out their gravitational effect on large scales, leaving only a tiny remnant. This would be like a vast, chaotic crowd of people pushing in every direction at once. From the inside, the noise is deafening. But if you step back and view the crowd from a distance, the net movement is almost zero. The vacuum's gravity could be a similar illusion of perspective, where the local frenzy sums to a cosmic stillness. These are not mature theories, but thought experiments that highlight the fragility of our assumption. They force us to ask if we have been too naive in stitching our theories together. The error of 120 orders of magnitude is so vast it signals not a minor miscalculation, but a profound misunderstanding of how the pieces of reality connect. This leads to an even broader reconsideration. Perhaps Einstein's theory of general relativity itself, while flawless in our solar system and in galaxies, requires modification on the vast scales of the entire cosmos. Just as Newton's gravity needed an update for strong fields and high speeds, our current gravity might need refinement for the universe as a whole. Theories of modified gravity attempt to tweak Einstein's equations on cosmic scales to produce accelerated expansion without any dark energy or vacuum energy at all. The cosmological constant would be an illusion caused by our using the wrong gravitational rulebook for the largest playground. These models face severe challenges, particularly in matching all the precise data from the cosmic microwave background and large-scale galaxy structures. But they represent a courageous direction, questioning whether the vacuum catastrophe is a sign that we have misdiagnosed the symptom, attributing it to an energy in space when the real issue is how space itself behaves on grand scales. Ultimately, the most hoped-for resolution lies in a theory of quantum gravity, a framework that does not force a marriage between two incompatible theories, but births a single, unified description from the start. In such a theory, concepts like the energy of empty space would be defined from first principles. String theory and loop quantum gravity, the two leading contenders, both aim for this. In these frameworks, the very notion of spacetime as a smooth continuum breaks down at the tiniest scales, replaced by vibrating strings or discrete loops of geometry. In that realm, the idea of summing up infinite contributions from point-like particles becomes meaningless. The question of vacuum energy is reformulated in a language where the old quantum field theory calculation simply does not apply. The catastrophe, in a sense, would be dissolved because the ingredients that created it, the point particles and the smooth spacetime they inhabit, are revealed as approximations of a deeper truth. We would find that we had been asking the wrong question with the wrong tools. The promise is that a successful theory of quantum gravity would naturally predict a small cosmological constant, or perhaps even zero, with any tiny residual value arising from complex topological features of the universe. We are not there yet. The final answer remains hidden, but the sheer magnitude of our error is a blazing signpost. It tells us we are missing something fundamental, a principle that governs the nothingness from which everything emerges. The vacuum catastrophe is not just a puzzle to be solved, it is a guide pointing the way to the next great revolution in physics. But this tangible proof of the quantum vacuum may not be what it seems. The Casimir effect is often presented as the ultimate demonstration of zero-point energy, a direct measurement of the quantum foam's pressure. The classic setup is elegant. Take two perfectly smooth, neutral metal plates and place them parallel to each other in an otherwise empty vacuum chamber, separated by a microscopic gap. As the plates are brought incredibly close together, a faint but measurable force pulls them together. The traditional explanation is beautiful in its quantum logic. In the empty space between the plates, only certain wavelengths of virtual particles can flicker into existence, those whose wavelengths fit perfectly as multiples of the gap distance. Outside the plates, all wavelengths are possible. This creates an imbalance in the quantum pressure. The greater activity outside pushes the plates together, a force generated purely by the restriction of nothingness. It seems like incontrovertible evidence that the vacuum is alive with energy, and we have measured its push. This demonstration is a staple of physics lectures, a concrete anchor for the abstract idea of vacuum energy, and it is frequently cited as a direct link to the cosmological constant problem. If we can measure the vacuum's energy here in a lab, the reasoning goes, then its gravitational effect on the cosmos must be real. But the story is far more nuanced, and this very nuance reveals a deep fissure in our understanding. There exists a powerful alternative interpretation that calculates the exact same attractive force without ever mentioning vacuum fluctuations. This interpretation treats the plates not as perfect mirrors for virtual photons, but as collections of real, fluctuating atoms. Every atom has a cloud of electrons that jitters slightly, creating a tiny, instantaneous dipole moment. This dipole induces a corresponding dipole in a neighboring atom, leading to an attractive force known as the van der Waals interaction. It is the same basic force that allows geckos to walk on walls. In the Casimir setup, when the plates are extremely close, these atomic interactions become relativistic and long-ranged, weaving a complex web of attraction between all the atoms in one plate and all the atoms in the other. This approach, using the established framework of quantum electrodynamics applied to the materials themselves, predicts an attractive force between the plates. And the number it predicts is, for many realistic experimental conditions, identical to the number derived from the vacuum fluctuation picture. so we have two completely different roads leading to the same destination. One road is paved with the ghostly energy of empty space. The other is paved with the well-understood quantum dances of electrons within atoms. This creates a profound ambiguity. If the force can be perfectly explained by atomic interactions, do we need to invoke the vacuum energy at all to understand the experiment? The debate is active and technical within the physics community. Proponents of the material-based view argue that the vacuum fluctuation description is a useful mathematical shortcut, but the real physics is in the correlated movements of charges in the plates. They point out that in actual experiments, the plates are not perfect mirrors. They are made of specific materials like gold or silicon, and their detailed electronic properties must be accounted for. When you do this meticulously, the van der Waals type calculation often matches the data more fundamentally. This suggests the Casimir force might be a spectacular relativistic quantum mechanical interaction between matter, not a direct probe of the energy of nothingness. If that is true, it potentially weakens a key experimental link in the chain of logic leading to the vacuum catastrophe. It means our most famous lab demonstration of vacuum energy might be a red herring, a beautiful illusion explained by a different, if equally complex, mechanism. This does not make vacuum energy unreal. The Lamb shift and other phenomena still point to it, but it does highlight how difficult it is to isolate the pure gravitational effect of empty space from the complicated quantum behavior of the matter we use to measure it. The Casimir effect, rather than settling the argument, opens a door to a deeper question. Are we measuring the stage, or are we just seeing a complex reflection of the actors upon it? The quiet we measure today could be the echo of a much louder past. To understand how a universe can be left with a whisper, we must listen to the echoes of its infancy, to moments of profound transformation when the very fabric of reality changed state. These are cosmic phase transitions, akin to water freezing into ice or steam condensing into droplets, but on a scale that shaped everything. In the first searing moments after the Big Bang, the universe was a unified, symmetrical soup of energy and forces. As it expanded and cooled, it crossed critical temperature thresholds where this symmetry shattered, and the vacuum itself underwent sudden, dramatic shifts. One of the most significant was the electroweak phase transition. In that first trillionth of a second, when the universe was still unimaginably hot, the electromagnetic force and the weak nuclear force were a single, unified electroweak force. As temperatures plummeted past a critical point, this symmetry broke. The Higgs field, which had been hovering at a zero value, settled into a new, non-zero state everywhere in space. This event gave mass to fundamental particles like the W and Z bosons, separating the weak force from electromagnetism and defining the physics we know. But this shift in the vacuum state was not free. It released an enormous amount of latent energy, like the heat released when water freezes. This energy injection would have acted as a massive, temporary cosmological constant, a colossal push that could have violently curved spacetime. Another major shift came slightly later with the quantum chromodynamics, or QCD, phase transition. This is when the universe cooled enough for quarks and gluons, which had been roaming freely in a primordial plasma, to become confined together into protons and neutrons. The vacuum state changed again, releasing another vast reservoir of latent energy into the cosmos. Each of these monumental events contributed a huge, positive chunk to what we would call the vacuum energy density of their era. If you simply added them up, the universe should have been torn apart by their cumulative gravitational repulsion. Yet here we are. So how did the universe survive its own birth pangs? The answer proposed by this line of thinking involves a concept that feels almost like a cosmic cheat code. In the equations of general relativity, the cosmological constant is a free parameter, a number you can simply put in by hand. Physicists call this the bare cosmological constant. It is not derived from anything else, it is just a term in the equation. The idea is that this bare constant could have been set, at the very beginning of everything, to a huge negative value, perfectly counterbalancing the huge positive energy that was about to be released from these phase transitions. Imagine preparing for a flood by first digging a canyon of exactly the same volume. As the waters pour in, they fill the void, leaving the surface calm and level. In this view, the bare constant is the pre-dug canyon. The energy from the electroweak transition pours in, and it is cancelled. The energy from the QCD transition follows, and it too is cancelled. Each cataclysmic release from the changing vacuum is met with a pre-arranged, opposing gravitational effect of precisely equal magnitude. After all the thunderous transformations are complete, after all the titanic energies have come and gone, what remains is the tiny, almost negligible mismatch between the negative bare constant and the sum of all the positive releases. That mismatch is the infinitesimal dark energy we measure today. This reframes the fine-tuning problem from a single, static miracle into a dynamic, serialized one. It was not one cancellation, but a sequence of them, each requiring a precision that defies belief. The bare constant had to be dialed to a value that would not only cancel the energy from the first transition, but anticipate and cancel the next and the next across the cooling history of the cosmos. The odds of this happening by random chance are, for all practical purposes, zero. It suggests a preparation so exact it feels orchestrated. This perspective does not solve the vacuum catastrophe, it deepens its mystery. It tells us the fine-tuning was not a one-time event, but a process woven into the unfolding narrative of the universe, a story where the void had to be calibrated with impossible care at every step just to end up almost, but not quite, silent. This impossible fine-tuning of the vacuum is not an isolated crisis. It echoes another, equally profound mystery that haunts the very heart of particle physics. This is the hierarchy problem, and understanding its parallel with the cosmological constant reveals a deeper pattern of fragility in our laws. Both problems share a disturbing structure. They involve a fundamental number that should be enormous, but is instead incredibly tiny, protected only by what seems like miraculous cancellation. The hierarchy problem centers on the Higgs boson, the particle that gives others mass. In the Standard Model, the Higgs has a measured mass of about 125 gigaelectronvolts. This is a relatively small mass on the grand scale of particle physics, but here is the puzzle. The Higgs field interacts with every massive particle in the universe. Through quantum loops, virtual top quarks, W bosons, and other heavy particles should constantly contribute huge corrections to the Higgs mass, pushing its value up toward the highest energy scales like the Planck scale. These quantum corrections are not small tweaks, they are titanic, on the order of 10 to the power of 19 times larger than the actual measured mass. For the Higgs mass to end up as small as it is, these enormous positive contributions must be cancelled out by equally enormous negative contributions with breathtaking precision, to about 1 part in 10 to the 17th power. It is like balancing the weight of a mountain on one side of a scale with a feather on the other, and having the scale read perfectly level. This is not natural in the language of physics. It demands a symmetry or a mechanism to protect this small number from the ravages of quantum corrections. Proposed solutions to the hierarchy problem often involve introducing new physics just beyond our current reach. Technicolor theory suggested the Higgs was not a fundamental particle, but a composite of new, stronger forces. Supersymmetry, as we discussed, offered partner particles whose contributions would naturally cancel the large quantum corrections. Extra-dimensional models proposed that gravity appears weak to us because it is diluted across unseen dimensions, while other forces are confined to our familiar three-dimensional brain. Each of these ideas was an attempt to explain why the Higgs mass is so small without invoking absurd fine-tuning. Now, look at the cosmological constant problem. Its structure is eerily similar, just on a vastly larger scale. The natural scale for the vacuum energy density is the Planck density, around 10 to the 93 grams per cubic centimeter. The observed value is about 10 to the negative 27 grams per cubic centimeter. The quantum corrections to the cosmological constant are those 120 orders of magnitude too large. For the observed tiny value to emerge, an almost perfect cancellation must occur, a fine-tuning far more severe than even the hierarchy problem. It is the same pattern. A fundamental parameter sits at a value exponentially smaller than the scale at which quantum effects want to push it. This parallel suggests the two problems may not be separate. They could be symptoms of a single, deeper instability in our framework, two cracks emanating from the same fault line in reality. Perhaps a solution to one will illuminate the other. For instance, if extra dimensions explain the hierarchy of forces, they might also modify how vacuum energy gravitates. If a new symmetry protects the Higgs mass, it might also govern the energy of the void. Yet, so far, no proposed cure for the hierarchy problem has successfully resolved the vacuum catastrophe. Supersymmetry, as we saw, only reduces the discrepancy. Extra-dimensional models often struggle to produce a small enough cosmological constant without, once again, introducing their own fine-tuning. This twin crisis highlights something fundamental. Our current physics seems built on a knife's edge. The masses of particles and the energy of empty space are not just numbers we measure. They are delicate outcomes, seemingly balanced against a cosmic storm of quantum noise. Their unnatural smallness is a persistent clue, a message written into the fabric of reality that we are missing a crucial piece of the puzzle. The vacuum catastrophe and the hierarchy problem together are not just errors in a calculation. They are signposts pointing toward the same uncharted territory, where the rules of the very small and the geometry of the very large must finally and dramatically unite. This staggering theoretical impasse is why we must turn our eyes back to the sky. The next great leap in solving this mystery will not come from pure thought alone, but from an unprecedented wave of cosmic observation. A new generation of telescopes, some already gazing upward and others soon to launch, are designed to scrutinize dark energy with a precision we have only dreamed of. Their mission is to determine, once and for all, whether the energy of the void is a true constant or a fading whisper. The Vera C. Rubin Observatory, currently under construction in Chile, will perform a decade-long survey of the entire southern sky. Its immense mirror and giant camera will capture the images of billions of galaxies, mapping the cosmic web in 3 dimensions across vast stretches of space and time. By tracking how the distribution of galaxies has evolved over the universe's history, and by discovering thousands more of those crucial type 1 a supernova, it will measure the rate of cosmic expansion with razor-sharp accuracy. Simultaneously, the European Space Agency's Euclid satellite is already in space, creating its own ultra-precise map of the large-scale structure of the universe. It will peer back to when the cosmos was only a third of its current age, charting the subtle distortions in the shapes of galaxies caused by dark matter, which itself is sculpted by the push of dark energy. Then, later this decade, NASA's Nancy Grace Roman Space Telescope will join this cosmic detective squad. With a field of view 100 times larger than the Hubble Space Telescopes, Roman will conduct deep, wide surveys to measure the distances to millions of galaxies and supernova. It will also employ a powerful technique called weak gravitational lensing, observing how the gravity of foreground matter bends the light from background galaxies. This provides a direct measure of how cosmic structures, from galaxy clusters to vast voids, have grown over time. The repulsive push of dark energy suppresses this growth, so by measuring the clumpiness of the universe across cosmic epochs, Roman can gauge the strength of dark energy's influence. Together, these observatories will create a multi-pronged assault on the problem. They will measure not just how fast the universe is expanding, but how that expansion rate has changed throughout cosmic history with exquisite detail. They will tell us if the dark energy density has remained perfectly constant, as a true cosmological constant would, or if it has varied slightly, as a dynamic field like Quintessence would predict. In essence, they will characterize the symptom with phenomenal clarity. They will tell us the exact nature of the cosmic acceleration we observe. Yet, for all their power, these magnificent machines face a fundamental limit. They are measuring the effect, not the cause. They can tell us whether the quiet hum is steady or fading, but they are not designed to explain why that hum is 120 orders of magnitude quieter than our quantum calculations suggest. They can constrain the models, ruling out entire families of theoretical ideas about dynamic dark energy, but they cannot directly probe the quantum vacuum itself or reveal the new physics that reconciles gravity with the quantum world. The observations from Rubin, Euclid, and Roman will be transformative, painting the most detailed portrait of dark energy we have ever had. They may well confirm that it behaves exactly like Einstein's cosmological constant, or they may shock us by revealing it is something stranger, something that changes. Either result will be a monumental step forward, but it will be a step that defines the mystery more precisely, rather than solving it outright. The chasm between the quantum and the cosmic will remain, waiting for a theoretical revolution that these observations can guide, but not deliver on their own. The data will sharpen the questions, making the vacuum catastrophe an even clearer target for the next generation of thinkers. String theory offers one of the most mathematically intricate paths toward that revolution, and its implications for the vacuum are both vast and bewildering. At its heart, string theory replaces the point-like particles of the Standard Model with tiny, vibrating loops of energy. The different vibrational patterns of these strings correspond to different particles, like notes on a guitar string. To be mathematically consistent, however, string theory requires more dimensions than the 3 of space and 1 of time we experience. It suggests there are 6 or 7 extra spatial dimensions, curled up into shapes so small we never notice them. The geometry of these hidden dimensions is everything. It determines the properties of our 4-dimensional world, the strengths of forces, the masses of particles, and crucially, the energy of the vacuum. When theorists began cataloging the possible shapes for these extra dimensions, they made a staggering discovery. The number of stable configurations was not 1 or a handful, but perhaps 10 to the power of 500. This is the string theory landscape, a cosmic library of unimaginable size where each book describes a universe with a unique set of physical laws and constants. In this landscape, the value of the cosmological constant is not a fundamental prediction. It is a page number, an arbitrary output of which compactification geometry you happen to have. Our universe, with its peculiarly tiny dark energy, would simply be one volume among an almost infinite collection. This landscape directly fuels the anthropic multiverse concept. If every possible vacuum state exists somewhere in a greater multiverse, then we inevitably find ourselves in one of the exceedingly rare bubbles where the constants allow for complexity and life. The vacuum catastrophe, from this vantage point, is not a problem to be solved by a single equation, but a selection effect we are doomed to observe. For many, this feels less like a solution and more like a philosophical retreat, exchanging a scientific mystery for an untestable, metaphysical one. Yet the story does not end with a static landscape of possibilities. More recent developments have added a provocative new layer, a set of ideas known as the Swampland Conjectures. Think of the landscape as an island of consistent theories that can be realized within a full theory of quantum gravity, like string theory. Surrounding this island is a vast swamp of effective field theories that look perfectly sensible on their own, but cannot be completed into a consistent theory of quantum gravity. They are dead ends, theories that seem to work at low energies but contain hidden contradictions that would appear at higher energies or when coupled to gravity. The Swampland program attempts to draw the map, to establish criteria that any viable effective theory must satisfy to stay on the island and not sink into the swamp. Some of these conjectures have direct, dramatic implications for dark energy. One prominent Swampland criterion suggests that a stable, positive cosmological constant that is truly constant might be impossible. In the full landscape of quantum gravity, the vacuum energy might not be allowed to be a fixed positive number. Instead, to be consistent, any form of dark energy must be dynamic, like a quintessence field that slowly rolls over time. Furthermore, another conjecture implies that the value of this field's potential cannot be too small or too flat. This challenges the extremely fine-tuned, shallow potentials often used in quintessence models, potentially ruling them out as well. The most striking possibility arising from this line of thought is that the true cosmological constant, the energy of empty space from quantum field theory, might be exactly zero due to some yet unknown fundamental principle. The accelerating expansion we see would then have to be driven entirely by something else, perhaps a dynamical field whose energy is masquerading as a constant for now, or even a modification of gravity on cosmic scales. The Swampland ideas turn the problem inside out. Instead of trying to explain a small number, they ask whether the small number we think we see is even allowed by the deeper laws of physics. It is a cutting-edge theoretical filter, suggesting that our current best-fit model of cosmology, with its simple cosmological constant, might actually reside in the swamp, fundamentally incompatible with a complete theory of quantum gravity. This represents a thrilling and contentious direction. It moves beyond accepting the landscape to actively constraining it, using quantum gravity not as a source of infinite possibilities, but as a guide for what is physically possible in our universe. The vacuum catastrophe, therefore, becomes the crucible for testing these very conjectures. By measuring dark energy with ever greater precision, we are not just characterizing the universe. We are probing the shoreline between the island of consistent reality and the surrounding swampland, searching for clues to the deepest laws of all. The most radical escape from this crisis may require us to abandon a core intuition about reality itself. For centuries, we have believed the universe is a three-dimensional volume, a container where things happen. But a startling idea from the frontier of quantum gravity suggests this is an illusion. This is the holographic principle, and it proposes that all the information contained within any region of space, every particle, every force, every bit of energy, is actually encoded on its two-dimensional boundary, like a cosmic DVD. The three-dimensional world we experience would then be a projection, a hologram generated from data stored on a distant surface. This is not science fiction. It emerged from the study of black holes, where physicists found that the maximum entropy, or information content, of any region scales not with its volume, but with the area of its enclosing surface. A black hole's entropy is proportional to its event horizon's area, not the volume inside it. This hinted that the true degrees of freedom of a system reside on its boundary, not within. If this principle applies to the entire cosmos, it forces a complete rethink of fundamentals like gravity and vacuum energy. In such a framework, gravity is not a fundamental force in the traditional sense. It emerges along with spacetime itself from the complex entanglement of quantum information on the cosmic horizon. Think of the smooth force of gravity not as a primary ingredient, but as a collective effect, like the pressure of a gas emerging from the chaotic motion of countless molecules. Physicists like Eric Verland have developed this line of thought into a theory of emergent gravity. In this view, what we perceive as the gravitational attraction of dark matter might actually be a consequence of the way information on the boundary of the universe changes as ordinary matter moves within it. The equations of gravity arise naturally from this informational interplay. This perspective turns the vacuum catastrophe inside out. The vacuum energy calculated by quantum field theory is a local concept. It sums up the quantum jitter at every point in three-dimensional space. But if reality is fundamentally holographic, if the true physics lies on a two-dimensional surface, then applying a three-dimensional calculation to find the energy of the void is a profound category error. It is like trying to understand a movie by grinding up the DVD and analyzing the plastic. The information for the picture is there, but you are looking at it in entirely the wrong way. The roaring quantum ocean of energy predicted by our local field theories might be a mirage, an artifact of using the wrong rulebook for a universe that is, at its most fundamental level, a hologram. The tiny cosmological constant we measure would then not be the remnant of a miraculous cancellation. It would be a feature of the emergent, three-dimensional world we inhabit, a consequence of how information is encoded and processed on the cosmic boundary. The 120 order of magnitude gap would dissolve, not because we found a better cancellation mechanism, but because we realized the two numbers were never describing the same thing in the same language. One is a miscalculation based on a false premise of locality, while the other is a measured property of an emergent reality. This does not make the cosmological constant any less real in our experience, but it completely changes its origin story. Of course, the holographic principle remains a theoretical framework, a breathtaking possibility rather than a proven fact. Translating its profound mathematical beauty into testable predictions for our specific universe is an immense challenge. Yet it represents the kind of paradigm shift the vacuum catastrophe seems to demand, a willingness to question not just our equations, but our most basic assumptions about what space, information, and energy truly are. It suggests that the solution may not be found within the universe as we see it, but in understanding the screen upon which it is projected. The vacuum catastrophe forces a choice between two visions of reality, each with profound consequences for how we see our place in the cosmos. On one side lies the staggering possibility of fine-tuning. This is the idea that the fundamental constants of nature, like the cosmological constant lambda, appear to be dialed to values within an impossibly narrow range that allows for stars, planets, and life. If the vacuum energy were even slightly larger, the universe would have blown itself apart before any structure could form. If it were slightly more negative, everything would have collapsed long ago. The precision required is beyond comprehension, like balancing a pencil on its tip for billions of years. From this perspective, our existence seems like a miracle of cosmic proportions, a lucky break so unlikely it feels intentional. It challenges the very notion that the universe is a product of blind, mechanistic laws, suggesting instead a preparation of almost artistic care. The alternative is to reject this improbability as an illusion. In this view, our current theories are incomplete. There must be a deeper, undiscovered physical law or symmetry that naturally, inevitably leads to a small cosmological constant. The vacuum energy is not fine-tuned, it is forced by a principle we have yet to uncover. This law would make a life-permitting universe not a lucky accident, but a logical outcome. The quest then is not to marvel at coincidence, but to discover the missing rule that makes the quiet void inevitable. This dichotomy cuts to the heart of the scientific endeavor. For centuries, physics has thrived on reductionism, the powerful idea that to understand the whole, you break it down into its smallest parts. We explain chemistry with atoms, atoms with particles, and hope to explain particles with strings or loops. The universe, in this view, is built from the bottom up, but the vacuum catastrophe resists this approach completely. The property of empty space, a cosmic scale phenomenon, cannot be derived from the sum of its quantum parts. The bottom-up calculation fails by 120 orders of magnitude. This suggests that cosmology, the study of the whole, cannot be merely an application of particle physics. The universe may have properties that only make sense in their totality, emerging from the global structure of spacetime in ways that cannot be seen by looking at any individual piece. Perhaps we need a top-down approach where the conditions of the entire cosmos constrain the laws within it. The debate over the multiverse is a direct outgrowth of this tension. If you find the fine-tuning too incredible to accept as brute fact, and if no single law seems forthcoming, the multiverse offers a third way. It replaces a single, fine-tuned universe with a nearly infinite array of all possible universes. In such a vast landscape, a handful of habitable worlds are statistically inevitable. We are not special, we are simply here, but this shifts the burden of explanation. The question changes from why are the constants right for life to why do we find ourselves in this particular bubble. For many scientists, this feels like moving the goalposts out of the observable universe. A theory that posits an infinity of unseen realms is notoriously difficult to test, pushing against the very definition of science as a process grounded in observation and falsification. Does the multiverse represent a bold expansion of scientific thought or a retreat into untestable metaphysics? The vacuum catastrophe does not just highlight a numerical error. It exposes a rift in our understanding of what an explanation even is. Are we searching for a unique, elegant equation that describes our one universe, or are we mapping a vast landscape of possibilities where our local laws are just one page in a near-infinite book? The answer will determine not just the future of physics, but our fundamental story of why anything exists at all. The silence of empty space asks the loudest question we can possibly face. The vacuum's quiet hum today stands in stark contrast to the universe's first explosive act. To find a vacuum energy density of truly cosmic proportions, we must rewind to the first fraction of a second after the Big Bang, to an era of unimaginable expansion called cosmic inflation. The leading theory suggests that our entire observable universe was once a microscopic quantum fluctuation, inflated to macroscopic size in less than a blink. The engine for this phenomenal growth was a temporary, colossal vacuum energy. A theoretical field, the inflaton, became trapped in a high-energy state, like a ball perched high on a hill. In that state, it filled every point in space with an immense, repulsive energy density, acting as a cosmological constant of staggering magnitude. This energy did not come from matter or radiation. It was a property of space itself, a false vacuum energy that caused spacetime to expand at an exponential, faster-than-light rate. For that fleeting moment, the vacuum catastrophe's prediction would have seemed almost reasonable. Then, as the universe cooled, the inflaton field found its way to a lower energy state. It rolled down the hill, and in doing so, released all that stored vacuum energy in a fiery burst, reheating the cosmos into the hot plasma of particles that would eventually form everything we see. The inflation field's energy decayed away, its job complete. This story presents a breathtaking duality. The same kind of energy that today is a faint whisper, 120 orders of magnitude too small, was once the dominant force in creation, powerful enough to stretch a subatomic speck into a cosmos. So we are left with a profound question. If the vacuum can hold such titanic energy to start the universe, why does it now hold so little? The inflationary epoch seems to demonstrate that our physics can accommodate a huge cosmological constant, but only as a transient, unstable state. Our current dark energy, by contrast, appears stable and persistent. This suggests the mechanisms that govern vacuum energy in the early universe and those that govern it today might be entirely different, with no clear bridge between them. This disconnect deepens with another eerie coincidence, often called the "why now" problem. Measurements show that the density of dark energy in the universe is, at this very moment in cosmic history, roughly comparable to the density of all matter, both dark and normal. This is strange because these two densities evolve in completely different ways. As the universe expands, matter density drops rapidly. Dark energy density, if it is a true cosmological constant, stays the same. For billions of years, matter was overwhelmingly dominant. For billions of years in the far future, dark energy will be virtually alone. We happen to live in the brief sliver of cosmic time, a window lasting only a few billion years, where the two are of the same order of magnitude. It is as if we looked at a century-long movie and found the most dramatic scene playing at the exact minute we pressed play. This temporal coincidence feels significant, another layer of fine-tuning that begs for an explanation. Perhaps it is a clue. Some theorists speculate that today's dark energy is not a constant, but a very slow rolling field, a distant cousin of the inflation. In this view, the "why now" moment occurs naturally when such a field's energy density finally drops to match the declining matter density. Others wonder if the ending of inflation and the nature of today's dark energy are linked by a deeper principle we have yet to uncover, a cosmic rhythm where vacuum energy transitions between different phases. While no concrete link has been established, these parallels remind us that the vacuum catastrophe is not an isolated error in a static universe. It is part of a dynamic cosmic story, a tale of energy that transformed from a roaring firestorm at the dawn of time into the faintest ember glowing in the present-day dark. The sheer depth of this crisis has pushed theoretical physics into a realm of profound creativity, where even the most unconventional ideas deserve a hearing. Beyond the well-trodden paths of supersymmetry or the multiverse, researchers are sketching blueprints for reality that challenge our most basic assumptions. One such intriguing proposal is called unimodular gravity. This is not a new theory, but a subtle reformulation of Einstein's own general relativity. In standard gravity, the equations treat all components of the metric, the mathematical description of spacetime, as independent variables. Unimodular gravity imposes a single, simple constraint from the start. It requires the determinant of the metric to be a fixed number, essentially saying that the volume measure of spacetime is predetermined. This might sound like a technical tweak, but its consequences are startling. In this framework, the cosmological constant, lambda, no longer appears as a fundamental constant of nature written into the laws. Instead, it emerges as an integration constant, a free parameter that arises only when you solve the equations for the entire universe. It is akin to the constant of integration you get in calculus, a number not set by the local rules but by the global boundary conditions of the problem. This reframes the fine-tuning issue. The question shifts from why is this fundamental constant so small to why did the universe choose this particular solution from the infinite set of mathematical possibilities. While it does not solve the magnitude problem outright, it changes its nature, suggesting lambda might be more a feature of our cosmic history than a fixed law. Another radical line of thought asks if the catastrophe could be diluted by sheer numbers. The prediction's enormity comes from summing contributions from a limited set of quantum fields. But what if the universe contains not just the few dozen fields of the standard model, but an astronomically vast number of them, perhaps even an infinite spectrum? In such a naturalness scenario, each field contributes a random amount to the vacuum energy, some positive, some negative. With a sufficiently huge and diverse ensemble of fields, statistical averaging could occur. The law of large numbers might drive the net result toward zero, much like the average height of a vast, randomly selected population clusters around a central value. The tiny value we see would then be the residual fluctuation, the slight imbalance left over after near-perfect statistical cancellation. The challenge here is that to achieve a cancellation to 1 part in 10 to the 120, you need an unimaginable number of fields and a mechanism to ensure their contributions are truly random and independent. It is an idea that trades one vast number for another, proposing a universe of breathtaking complexity beneath the surface to explain its apparent simplicity. The possibility of extra dimensions central to string theory offers another escape route. In some brainworld models, our entire three-dimensional universe is a membrane floating in a higher dimensional space called the bulk. In these pictures, the fundamental scale of gravity is much larger in the bulk, but gravity itself is a weak force in our world because its influence leaks out into the extra dimensions. This leakage could also apply to vacuum energy. The enormous quantum vacuum energy we calculate might primarily gravitate in the bulk, having only a tiny, diluted effect on our brain. Our perceived cosmological constant would be just the faint shadow of a much larger energy existing in a higher dimensional space. This geometrizes the problem, embedding it in the architecture of reality itself. Similarly, a more recent and highly specific proposal is called vacuum energy sequestering. This mechanism introduces a new principle where the universe dynamically adjusts its response to vacuum energy. It proposes that the cosmological constant is not fixed, but is determined by the average matter density across the entire history of the cosmos. The idea is to make lambda sensitive to the global content of the universe, so that if the intrinsic vacuum energy were huge, the equations would automatically generate a counterterm to cancel most of it out, leaving a small residual tied to the matter we actually see. It is a bold attempt to let the universe self-tune, though it requires modifying gravity in a very particular, global way. These are just glimpses of a sprawling frontier. The vacuum catastrophe is so severe, so resistant to conventional fixes, that it has become a catalyst for extraordinary speculation. The field is actively exploring these highly creative avenues not because they are likely, but because the standard paths have led to a cliff edge. When the best theories in human history disagree by 120 orders of magnitude, it is a clear signal that something fundamental is missing. So physicists are willing to question everything, from the constancy of constants to the very dimensionality of space, searching for the lever that will move this immovable problem. Each idea, no matter how speculative, is a different angle of attack on the same profound mystery, a testament to the fact that in the face of such a colossal error, no thought is too strange to consider. This single number, 120 orders of magnitude out of place, stands as the most glaring unsolved problem in fundamental physics. After this entire journey through quantum foam and cosmic expansion, through elegant symmetries and radical multiverses, we must return to a simple, humbling fact. We have no answer. Our most sophisticated telescopes can map the effect of dark energy with breathtaking precision, yet its microscopic origin remains a complete mystery. We can describe the whisper of the void, but we cannot explain why it is so quiet. This is the enduring power of the vacuum catastrophe. It is not a puzzle on the periphery. It is a gaping wound at the very center of our understanding, where our two greatest theories meet and fail. That we can be so spectacularly right about so much of the universe, from the spin of an electron to the curvature of light around a galaxy, and yet so catastrophically wrong about the energy of nothingness, enforces a profound humility. It reminds us that our maps of reality, for all their detail, are still incomplete. The resolution to this crisis will not come from a minor adjustment or a clever tweak. The chasm is too vast. Mending it will likely require a revolution as profound as those sparked by quantum mechanics or relativity themselves. It will demand a new way of seeing, a framework where the very large and the very small are woven together from the start, not stitched together in desperation. This pursuit, the drive to understand why the cosmos is the way it is, continues to define the frontiers of cosmology and theoretical physics. It is a reminder that our greatest errors often point the way to our next great truths. So as you look up at the night sky, remember that the deepest mystery is not in the distant stars, but in the vast, silent space between them. Stay curious about that silence, for within it may lie the key to everything.